Stop scrolling. I need you to imagine something impossible for a second. Imagine you are locked inside a room with no doors and no windows. In our world, the real world, you are stuck. You can't just walk through the wall, right? That would be magic. But in the world of quantum physics, subatomic particles do this all the time. It's called quantum tunneling. They don't climb over the wall. They literally pass through it like ghosts. For 100 years, we thought this ghost mode was strictly for the tiny stuff, atoms, electrons, things you can't see. We thought that once things got big enough to touch, the magic stopped. Well, the 2025 Nobel Prize in Physics just proved us all wrong. They didn't just find a new particle, they proved that quantum weirdness can happen to objects big enough to be man-made. So how did they force a microchip to break the laws of reality? And what does this mean for the supercomputer in your pocket? To understand why this Nobel Prize is such a monumental deal, we have to go back to a thought experiment that has haunted physicists since 1935. Schrodinger's cat. You know the story. You put a cat in a box with a radioactive atom and a vial of poison. If the atom decays, the poison releases and the cat dies. If it doesn't, the cat lives. Quantum mechanics says that until you open the box, the atom is in a superposition. It is both decayed and not decayed. Therefore, logic dictates the cat is both dead and alive at the same time. It sounds cool, right? But Erwin Schrödinger actually came up with this idea to mock quantum mechanics. He was basically saying, look how stupid this theory is. Cats can't be zombies. Biology doesn't work like that. And for nearly a century, he was right. Here is the problem. We live in the macroscopic world, the world of coffee cups, cars, and cats. In our world, things follow classical physics. A cup is either on the table or on the floor. It is never in both places at once. Why? Because of a brutal phenomenon called decoherence. Think of a quantum state like a delicate soap bubble floating in the air. It's beautiful and perfect. But the moment it touches anything, a stray air molecule, a photon of light, a tiny vibration, pop, it bursts. It collapses into a single boring reality. The bigger an object is, the more atoms it has. The more atoms it has, the more it interacts with the environment. It is constantly being touched by the universe. The universe is like an aggressive paparazzi, constantly snapping photos of matter, forcing it to pick a pose. This is why we've never seen a chair tunnel through a wall. The environment observes the chair too intensely. The quantum magic dies before it can even start. So for decades, the physics community had a consensus. The quantum classical boundary is absolute. You can have quantum effects in a single electron, maybe a tiny molecule if you're lucky. But a man-made circuit? A chip visible to the naked eye? Impossible. The noise of the world would destroy the quantum state instantly. This was the wall that stood between us and the next technological revolution. We were stuck. We knew quantum mechanics was the operating system of the universe, but we were locked out of the admin panel because our fingers were too big to type on the keyboard. That is, until Clark, DeVoe, and Martinez decided they didn't care about the rules. They asked a question that sounded insane in the 1980s. What if we built an artificial atom? What if we built a circuit that is huge, billions of times larger than an atom, but we isolate it so perfectly from the noise of the universe that it forgets it's a machine and starts acting like a ghost? This wasn't just an engineering challenge, it was a philosophical war against nature itself. They had to build a device that could sit in our world, but behave as if it lived in the quantum realm. They had to silence the paparazzi.
So, how do you silence the universe? How do you build a box so quiet that a microchip starts hallucinating? The 2025 Nobel laureates, Clark, Deverett, and Martinez, realized you can't just use regular electronics. Regular wires have resistance. Resistance creates heat. Heat is vibration, and vibration is the death of quantum magic. To beat the game, they had to go superconducting. They cooled aluminum and niobium circuits down to near absolute zero. We are talking 20 millikelvins. That is colder than the deepest void of outer space. At these temperatures, electricity flows with zero resistance. The electrons stop bumping into things and start marching in a perfect synchronized army, forming what's called a Cooper pair condensate. But cooling it down wasn't enough. A cold wire is just a cold wire. To make it behave like an atom, they needed a nonlinear element. They needed a magic door. Enter the Josephson junction. Imagine a regular pendulum, like a child on a swing. It can swing at any height. That is classical physics. But an atom is different. It has specific energy levels. It's like a ladder. You can stand on step 1 or step 2, but you cannot hover between them. The Josephson junction, a tiny insulating barrier sandwiched between two superconductors, forces the electrical circuit to act like that ladder. It turns a macroscopic circuit board into an artificial atom. It forces the billions of electrons to behave as a single quantum entity. Now, here is the moment that won them the Nobel Prize. In the pioneering experiments, they trapped this electrical state in a potential well. Imagine a ball stuck in a valley. To get to the next valley, the ball has to roll up the hill and down the other side. In classical physics, if the ball doesn't have enough energy to roll up the hill, it stays in the valley forever, period. Clark and his team watched this flux, the magnetic state of the circuit. They knew it didn't have enough energy to climb the hill. They watched and they waited. And then it happened. The signal vanished from the first valley and instantly reappeared in the second one. It didn't climb the hill. It didn't roll over it. It went through it. Macroscopic quantum tunneling. For the first time in history, we witnessed a macroscopic object, something you could technically see under a microscope, defy the laws of classical physics. It was a ghost in the machine. This wasn't just a cool trick. This was the birth of the superconducting qubit. Michel Deverett and John Martinis took this discovery and engineered it into the high-fidelity quantum processors we see today. Every time you hear about Google's Sycamore or IBM's Eagle processors, you are looking at the direct descendants of that first tunneling experiment. They proved that the boundary between the quantum world and the real world isn't a brick wall. It's a blurry line that we can manipulate. They showed us that if you treat nature gently enough, even a microchip can dream.
So why does this matter to you? Why should you care that a few scientists made a circuit act like a ghost? Because the 2025 Nobel Prize isn't just an award for a cool experiment. It is the official certification of a new era. We have transitioned from the observation age to the control age. For the entirety of human history, we were passive observers of the quantum world. We watched the stars, we smashed atoms, and we wrote down what happened. But we were always on the outside looking in. Clark, Deverett, and Martinez didn't just look, they reached in. By proving that macroscopic objects can tunnel, they handed us the keys to the quantum computer. Think about it. The computer or phone you're using right now processes information in bits, zeros and ones. It's linear, it's safe, it's slow. But a machine built on macroscopic quantum tunneling, using those artificial atoms, doesn't just calculate, it explores parallel possibilities. It can simulate molecular bonds to discover drugs that cure cancer in days instead of decades. It can design batteries that never die. It can crack encryption codes that would take a normal supercomputer the age of the universe to solve. This Nobel Prize tells us that the magic of the universe isn't locked away in the subatomic realm. It's right here. It's scalable, and it's engineering ready. But perhaps the biggest takeaway is philosophical.
We used to think there was a hard line separating us from the quantum weirdness. We thought we were too big, too noisy, too real to be ghosts. This discovery shatters that ego. It reminds us that at our core, everything, from the microchip in your phone to the neurons firing in your brain, is built on a foundation of uncertainty and probability. The wall between the magical and the mundane doesn't exist. We just didn't know how to look at it properly. So, the next time you feel like you're stuck, like you've hit a wall in your life, remember the lesson of the 2025 Nobel Prize. If you can just quiet the noise around you, if you can find that perfect coherence, you don't have to climb the wall, you can just walk right through it. Thanks for watching.